Hi, so this is a lab 4 of physics and we focus on oscillations. In the introduction of this lab, the purpose of this lab was to track and analyze the motion of a spring mass system with an oscillation pattern of an arc, and the goal was to determine whether the computational model, which follows the collected data from the tracker, properly follows the energy principle. And so how I went about this lab was utilizing tracker to track the observed position of the mass, and I also utilized GlowScript to establish a computational code that predicts the graphs, the object's motion, and the changes in energy. And then the result of the lab was that the lab demonstrates the energy principle as the system's total energy remains at zero. So these were some of the fundamental principles I used. So I utilized Newton's second law, the energy principle, and formulas derived from the Newton's second law, as you can see here. And so for lab 4 specifically, the free body diagram, you can see that the only forces acting on the spring was the force of the spring and the force of gravity, and therefore F net equals force of the spring plus force of gravity, or more specifically, this formula right here. And then for lab 4, the surroundings was nothing, and the system included the mass, spring, and earth. And since nothing's interacting with the system, we can assume the change in the system's energy is going to be equal to 0, and therefore kinetic energy, the change in kinetic energy plus the change in the potential energy of the spring plus the change in potential energy of gravity is equal to 0. And so these were the known values and the observed motion. As you can see, it's moving in an arc pattern right here. And so the mass of the object was 0.402 kilograms, the stretched length was 0.7 millimeters, and the initial position ended up being this according to my tracker analysis, and this was the initial velocity because it started from rest. So this is the graph of the movement along the x-axis over time, and this is the movement along the y-axis over time. And so how I took the periods was for it to be like T1, T2, T3, and T4 respectively. And so this was what I was referring to, T1, T2, T3, T4, to find like an average period, which I found to be 1.6145, and then I used this period to solve for the spring constant, and since the spring constant is included in this equation right here, I just isolated K, and it ended up being 6.088 Newton meters. And I also solved for the relaxed length of the spring using the F net formula. The spring force plus the force of gravity is equal to 0, and that length ended up being 0.0529 meters. And so the code is where I changed up some of the things. So you can see that I changed up the mass of the ball, the ball's initial position, and the ball's initial velocity. I also took the spring constant right here and the relaxed length right here, and then I also made these equations which was related to the ones I just said before, and also like formulas derived from Newton's second law. You can see I utilized over here, so kinetic energy, potential energy, and the change in energy of the system. Then you can see me including those principles over here as well. And I also utilized the tracker's position, like the x and the y, to create this graph. And so the predicted versus the observed. Predicted is in the blue and the observed is in the red. One thing to notice is that at first the graphs are like, though they do deviate, they're way closer together than at the end where they're completely pretty much different from each other. This is because in real life, or the observed data, the surrounding isn't isolated from the system. So the work done by friction between the spring and the pin, and there could be work done by the drag force, and therefore it would kind of change the graph from the predicted data. And that may also have been just because of human error, like placing the point of the mass of the system in tracker was not the most accurate. Getting into the questions, is the energy principle satisfied? My answer is yes. There is no net external force acting on the system. The change in energy, as can be seen here, is equal to 0. And there's also different types of energy, as shown over here. But the graph indicates that the total change in energy, so if you add all these up, it's a constant 0. But I also compared the x and y periods using GlowScript data. And so when I took, I did the same process of finding the period in the first one, but used these graphs instead. The period ended up being 1.6725, and therefore the spring constant ended up being 5.674 Newton meters, and in the y direction, it ended up being 1.61, and this ended up being 6.123 Newton meters. And so you can obviously see that finding the period using an x and y graph gave me two different values for the period and therefore the spring constant. And so my conclusion was that using different directions to find the period causes deviations in the period itself. This explains why the spring constant and the graphs differ from one another. And thank you for listening.